Okay, guys, we're getting to the home stretch here. Let's look at section 14.1. I'm going to go kind of quickly through this because I think that you'll see that it's pretty simple, even just reading through the notes. So we're going to talk about translations and rotations, which you already did some of this when we did our tessellations project. So it says a translation is one type of isometry. Any function from a plane to itself, that is a one-to-one correspondence in a transformation. So basically, a transformation is another word for a slide. Okay, so just imagine taking that figure and then just whoop, sliding it over. And sometimes it's denoted by A prime. So like if you take A and you slide it to a different location, that's called A prime. So here's an example of that. It just is talking about how we moved it a certain distance and moved this other guy at the same distance. And so this AB over here on the left, we moved it over. You see A prime, B prime is a translation of AB. Here's an example of translating AB to this blue line AB over here. And then, so again, I'm just taking this and then shifting it down. And they're just showing here that we went down 2 over 2, down 2 over 2. We did the same thing for each point. This is another way to talk about it. Don't let the equations confuse you. They're just saying, what are we doing here? We're going to go 5 to the right, and we're going to go 2 down. That's what this means. X plus 5. X is the horizontal distance, and Y is the vertical distance. So this just means right 5, and then that means down 2. So if you see that, that's what happens here. We go right 1, 2, 3, 4, 5, down 2, 1, 2. Then we took this point and we went right 5, down 2, and then here we went right 5, down 2, and then we make this new image. This pink triangle is the translation of that green triangle. Excuse me. That's what they're talking about. Here's another example of that with the square. So they show that translation here. And it's just practicing moving every coordinate. In this case, -2. And then for the x, that's horizontal. So this means left 2, and this means up 4. So you're taking every point, moving it left 2, up 4. And then here's the example of that. So if you check, we went left 2, up 4, left 2, up 4, left 2, up 4, left 2, up 4. And then this guy is that translation of the original square. A rotation is another kind of transformation. Rotation is when you rotate, most people know that term, about a point that's in the center. And you could either do that clockwise or counterclockwise. So here's an example of that. So I take AB and then I rotate it about the center O. And so if you look at that here, we're taking A and we're rotating it to this guy. So hold on, I'm recording something. I'm recording something. Maybe I'm recording something. Okay, in just a second. I'm recording something. Go out there. I'm almost done. I'm trying to do this real fast before I get your brothers. Thank you. Um, so we're just rotating this around about that point O. A rotation of 360 degrees is called an identity transformation because if you turn 360 degrees, you're right back where you started. Whereas a rotation of 180 degrees is a half turn. Okay, here's yeah, see, this is a rotation arrow. So if I rotate it 180 degrees there, but if I rotate it 360 degrees, you're back to where you started. And the translation is just moving it over. Okay, this is a translation. This is a rotation. Tessellations, you know about because we studied that for our project. This is talking about regular tessellations, regular polygons. an example of squares, equilateral triangles, and hexagons. And then this is talking about kind of what you guys did, that you were able to cut out a shape, move it over and tape it, and then that figure also tessellated. And so this is explaining that method here. And now this is saying, will a regular polygon tessellate? And to know if it will, we have to have an angle sum of 360 degrees. So that's just for a regular polygon to line up. These angles have to add to 360 degrees or they won't fit perfectly. So in this case, we have 3 pentagons surrounding the vertex. Are they going to tessellate? The answer is no, because for the interior angles of a pentagon are each 108 degrees. And so when you sum up 108 degrees, you don't get 360, so it doesn't work out. And the formula for that, if you see here, it's n minus 2 times 180 divided by n. So let me write that out. N minus 2 times 180 divided by the n. That gives you the degree of each angle in an n regular polygon. Okay, so what they did is they took 3, because n minus 2 is 3 times 180 divided by 5, and that gives you 108. And so that's the sum, that's the measurement of each of these 5 angles in a regular pentagon. Regular means that they're the same angle, same side length. And 108, all 3 of those together do not add up to 360, so it won't tessellate perfectly. So that's that. And then this is showing you the measure of the interior angle, which each of these is figured out by the formula I just told you. So that's where they're getting these guys from. But so that's the measure of an interior angle. Since 360 divided by a number greater than 120 is smaller than 3, and the number of sides of a polygon cannot be less than 3, no regular polygon with more than 6 sides can tessellate. So this is semi-regular, where you can see that they're made up of different polygons, not just one. Square, equilateral triangle, regular hexagon. One factor is the sum of the measures of the interior angles must be 360. So this is just showing examples of tessellations with other shapes. So that's section 14.1. I will do 14.2 shortly.